All right, yeah, thank you for including us in the meeting program, and thanks to the local hosts for putting on a great conference. I know that takes a lot of work, and we really appreciate your efforts. So my name is Doug Schuster, and there's a number of co-authors on this paper. We're going to take a big pivot, from some of these deep science talks and how we use reanalysis to look at kind of the broader aspect of how we can provide services to support use of reanalysis in other products. So briefly, I'll look at some of the existing data services landscape, review our emerging data services at NCAR as well as in the community, and then briefly talk about what you could do as a data producer really to make your data easy to reuse by others. So just a little bit of background on what NCAR is. It's the National Science Foundation funded National Center for Atmospheric Research. We're located in Boulder, Colorado. And it's a federation of a number of different labs that look at various aspects of some of the Earth system science components, from the effects of the sun on the Earth's atmosphere to the role of the ocean, weather, and climate prediction, as well as supporting and training the next generation of Earth system scientists. So a number of these talks have come from operational centers and institutions, and we're really focused on research and education. So historically, what we've done, there's a lot of talk in the community about data proximate compute. So data sets going into the commercial cloud, data sets going to places where you can basically visit them with your code versus having to move them around. So that's kind of been our strategy in our organization for a long time at NCAR, specifically in the Computation and Information Systems Lab that I represent. We've historically brought in reanalysis from producers so that those users that are on our HPC systems can compute and perform analysis directly on these products without having to move things around. So they really have good access to these products. And then we also have a service that some of you in the room might have used where you can actually access data remotely, and that's kind of a standard interface that you have. So this provides a number of options where you can move data to your local system as well as find what's available in our local HPC to support your research. But this is really a challenge this day and age. I've seen we see all the talks here, and I'm kind of thinking to myself, with all these analysis, how are people performing their analysis? Are they moving data around? Are they running on their personal computer? Are they running on some HPC system or the commercial cloud? Are you sharing your code so others can actually, build upon what you're doing? That's a big thing going on in open science these days. But the model that we've supported historically, characterizes as a legacy download and analyze model, as you've experienced, I'm sure, can be time-consuming and inefficient. With these real large products, it's really not feasible for most users to download and store hundreds, thousands of terabytes on your local system. And then each producer, in many cases, produces their own flavor of a format, so it's challenging for the end user to actually understand what they're getting from somebody, and they have to do a lot of cleaning even after they move that data to their local system. So this is one challenge that we're trying to address with what I'm going to describe. And then once again, I'll go back to our, on-prem, we'll call it our on-prem cloud users that have direct read access to all these different products. But unfortunately, that's limited to users with accounts that have access to our systems. I will point out, if you're from a U.S. university, you can get an account if we host any data set that you're interested in using on our HPC system. So I'd really recommend that versus downloading data. No matter who your funder is, you can get an account on these systems. And then there's insufficient search capabilities. So we have, products that include these retrospective reanalyses, observations from global providers, as well as we produce a number of field campaign products in our institution. So these are kind of unique products for specific use cases, and then climate model simulation future scenarios. So we've been following what's been going on in the community. Really lots going on in the private sector. We've heard a lot about the climate data store. And then many users really are starting to gravitate to what's going on in the commercial cloud in the US and in other places. So Google Cloud, for example, copied the full ERA5 reanalysis in its raw, T690, whatever it is, reduced Gaussian structure over to their storage. because, I mean, this obviously tells you there's value in it, otherwise they wouldn't do this. So it costs a lot of money to store this data. So they're paying for the storage and they're paying for the egress fees because they want that data in, and they have commercial customers that want to use that data. But anyway, they copied the whole thing over. I think they've got, over 6 petabytes of data in Google Cloud. And really one of their driving motivations is this WeatherBench application where you have a platform of these various data-driven forecast models that people can develop and train against ERA5 as one source of data. And then you have communities of practice that are out that are looking at some of these big data challenges. One's called the Pangeo Community of Practice that some of you might be familiar with, but they're developing tools and capabilities as a community where we can work together and share solutions for accessing and providing really performant analysis on some of these real large data sets. So what we're doing in our organization, is looking for data science infrastructure that connects, you could call them AI, analysis-ready geoscience data sets with community-developed analytics tools to allow users to share, integrate, analyze, and visualize geoscience research data to drive scientific discovery. And we're really building this on, some of those emerging solutions that are out there, like the Climate Data Store. What we want to do is broaden access to our on-prem compute capabilities, kind of our on-prem cloud, if you want to call that, to a larger number of researchers. And then we want to look into what's called streaming data analytics for remote users, so you don't have to follow necessarily that traditional web download strategy that you've used in the past. And then we would like it to be interconnected with commercial cloud providers and other providers as well. So if you need to burst data into the commercial cloud to do your workflow, you can do that. If you need to pull it into NCAR, you can do that. But ideally, in the long run, all of the storage infrastructure that there is out there will kind of look like one big block of storage, no matter where it's located geographically. So that's kind of the big picture. And, one component of this is observations. There's been a lot of passion in this meeting about observations. How do we use observation? We need more observations. What's quality control on observations? But all that being said, they're really challenging and hard to use with a variety of formats. They're messy. So I was happy to hear about the effort between NASA and NOAA in building an observations database. A lot of work at Climate Data Store on doing that. And we kind of want to do the same thing, abstract out some of the complexity so it's easier to use these observations in data assimilation research. Not every data assimilation research tool has to build their own bespoke solution to access these things. Maybe there's some common APIs and strategies that we can use. And then I'll get into next kind of the streaming access component. So one thing that we're working on, which is a National Science Foundation funded project, it's under something called the National Discovery Cloud for Climate, is integrating kind of our local infrastructure with what's called the Open Science Data Federation. And it's branded as a federated platform for delivering data sets from repositories to compute in an effective, scalable manner. And I think kind of the broad long-term goal with this that they're working towards is streaming data delivery and access, and kind of compute location agnostic storage. So no matter where you're computing, you can kind of pull data into your workflow from its various storage points in a performant way. So that's kind of what the big picture is with this initiative. So kind of looking at it small scale, we'll still have our on-prem cloud users that really have the most performant access to the data that's stored within our resources at NCAR. But then we want to support remote users with, their traditional download and analyze workflow, but then a streaming data analysis capability. Think of, in a scalable way. There's been some solutions for that, but some of these solutions don't really work with these really hundreds to terabyte, 100 terabyte, petabyte scale data sets. But think about some kind of a Netflix solution where you can have good, better, best resolution or something like that. What do you need for your data analysis? Not everybody needs the highest resolution. In fact, I'd argue most people don't necessarily need that for what they're doing. And then eventually, we hope to go to a landscape that looks something like this. That's a network of connected domain research data common systems and analysis platforms. I kind of mentioned it as compute agnostic storage. Hopefully you don't care where things are stored and you can access them in a performant way. and really abstract out a lot of complexities that there are with the underlying structures of data for the end users. They don't necessarily want to deal with that. So one thing that we did was hold a workshop, kind of looking at some of the community expectations for data commons. This involved mostly US university and agency representatives along with a few international partners. We had good representation from universities that are less resourced in the United States, coming from parts of the country in the United States where you can't actually even drink the water out of the infrastructure that's provided in those cities. So it was great to get a wide variety of viewpoints, on needs for this type of a facility. But, I think we've heard this in other talks, but you need multiple points for entry for novice, intermediate, advanced users. I'd say this group is really advanced users in general. But a lot of these community members, they enjoy using, Google Earth Engine, Google Colab, some of those tools. So how can we support them better with that type of experience? And then in terms of tools and services, they want this type of resource to be able to facilitate their creativity and innovation and bring their own containers to compute against data that's stored either in our facility or other facilities. So that's one idea. What can you do as a data producer? In the operational NWP communities, you have formats like Buffer and Grib. Well, outside of that community, nobody likes those formats. Maybe that's not, anyway. So if you can use some of these other formats, that's great, but I get why you need Buffer and Grib for operational NWP at this point. And then follow conventions. There's a lot of our own flavors of things we put into these formats, but if one producer characterizes, maximum temperature over a 6-hour window in a different way than a different producer, it's challenging for the end user to work with that stuff. And then, what do you need to preserve and for how long? It's actually costs a lot of money to preserve all this data. It's expensive. It has a CO2 footprint. And then in terms of what you're doing, do you need to store it in some kind of a resource that's co-located with community accessible compute? So those are some things to think about. And in many cases now, the private sector will pull it in because they have so many commercial customers that they'll bring it into a resource that has co-located compute. So that's kind of what's going on out there. With that, I'll conclude my talk. So thanks for your attention.